Start. Okay. So you switched off. Yeah, start. Okay. So we attended the last class. Okay. At that time, we give you the motivation for adaptive filter. We had some examples. Examples were taken, one from adaptive line enhancer. That was if you have got a sinusoid which is noisy and you have to filter out, you can use a bandpass filter. But if the frequency changes from time to time, then you cannot go on redesigning and re-implementing the filter. The filter should have the learning capability from the data, so that it adjusts its center frequency accordingly. So there should be an adaptive algorithm, adaptive mechanism, which will learn from the data and adjust itself. That was one example. Another example which I gave was from echo cancellation, which is very valid for telephone and data modem. That is when an incoming signal is coming, which could be either speech in the case of telephone modem, or more importantly, which could be data for data modem. Then instead of going to the receiver through the hybrid, part of the data comes back in the return circuit as an echo, which gets mixed up with the data flowing from this end already. So that gives rise to error. So then we model that hybrid as an echo generating system, as a linear FIR filter of very large order, and by using adaptive algorithm, what we did, we estimated, we identified those filter coefficients. So basically we emulated this hybrid performance. So we generated an echo and subtracted the echo from the incoming signal. That was, and then since hybrid characteristics changes from time to time, this has to be done adaptively. That was for adaptive line echo canceller. Another very important example, of course I cannot get into that now, very important example was discussed. Did I cover that fully, adaptive equalizer? So that where did I stop last time? Before noise. So quickly I will go through that example. That was adaptive equalizer, but those who are coming for the first time today, I cannot for their sake go back. Okay, so the channel model, this only I am telling you for the conception of those who are coming only for today, or joining today. This is only a discrete time model. This is not the actual physical channel. The model was this, that you are transmitting, suppose, some sequence I0, I0, I1, I2, I3 like that. Okay. So this I0, I1, they can take some discrete values from a set of some finite discrete values. That set is called alphabet. It has a finite number of symbols. If you are taking r bit together, so 2 to the power r symbols are possible, so 2 to the power levels. In general, this could be complex in phase and quadrature component, but for our business, we assume this to be real for our business here. And in IN, there is a then equivalent discrete time model of the channel, which we replace by HN. And what you get here is YN. Okay, or maybe I called it XN that day, right? What did I call it? SN, is it? Yeah, this is SN. This HN in general is non-causal, but that is coming because of the way it was generated, the symbols were transmitted. That is, you take a pulse, you trigger the pulse goes, you get pulse gets multiplied by a symbol say I0, and you measure it at the midpoint of the pulse at a point capital T. But even before that point arrives, you switch on the next pulse, maybe after a second of tau, at a gap of tau. So when you measure the first pulse height, second pulse already is present there. So contribution from future comes. That is how the non-causality came up. That is how this model came up. This is an equivalent model that was derived. This is not the physical channel. It is non-causal in general. And then the whole channel is noisy. There is an additive noise. Instead of showing it present all throughout, we take the entire noise effect and add it separately as a noise component, and you can call it Z n. So, this is what you receive R n. For the time being, if you assume that Z n is not present, for the time being if Z n is not present, then if H n is H z, Z transform, then what you do? You pass R n through, if you pass 1 by H z, you should get back your I n. Suppose Z n is not there, H z 1 by H z is the basic equalizer, it is called linear equalizer. Okay, linear equalizer is a linear system, but there is some problem in the sense, these are the things, I mean, not necessarily part of adaptive filter theory, but I am trying to convey this info to those who work in communication area. Okay, and these are not given elaborately in books. Okay. Normally, when this H n comes, you remember how the H n came? It came because of this, that suppose there is a pulse, then future pulses, past pulses, still past pulses, still future pulses, they all interfere here. Their interference goes down as the pulses are further and further away from the central pulse. The interference component is reflected by the coefficient. H 0 is the pulse height, okay, at the center point of the basic pulse. Initially, we set it to be 1, but the channel distorted it, so it became H 0. H 1 was the value of the future pulse, or maybe the past pulse, the immediately previous one, as it passes through the point, the center point, this much height. Then H 2, H minus 1, H minus 2, like that. So, you understand that this H sequence, since this is a repetition, I am going fast, all these we discussed in the previous class. Okay. H sequence is such, it is a dying sequence on either side. That is, H n could be like this. Okay. H n could be like this. Now, so you can approximate by a FIR filter, isn't it? By an FIR filter, only thing is this filter is non-causal, so you can place the origin here, all that is fine. So, FIR filter means it has got only zeros. So, if H z has zeros, 1 by H z only has poles, but there is no guarantee that the zeros of this filter or poles of this filter will lie within unit circle. Some could be within unit circle, some could be outside unit circle. So, 1 by H z is not necessarily causal, 1 by H z is in general stable, if stable filter, because any real time filter is a stable filter, but it is non-causal. That means 1 by H z, if the corresponding impulse response is H prime n for 1 by H z, how will H prime n look like? It will be going again in both direction, but it is a stable system. Stable means mod of H prime n, if you sum, it is finite. That means H prime n has to die out, it cannot remain steady, then it is not summable. For any stable system, impulse response is absolutely summable, means impulse response is always dying down. It has to be always dying down. In fact, all the in the analog case, if you deal with RC circuit, RL circuit, you see all those e to the power minus t by RC, RL t by L, e to the power minus, all those are dying. Those are basically impulse responses. They have to die out so that they are absolutely summable. So, that means this will die out. So, you can truncate it up to some point n minus 1, and on this side also, it is not necessarily symmetric on both sides, up to this. Okay. So, that means 1 by H z is this filter, and which is non-causal. Non-causal filter in general cannot be implemented, but suppose I shift the origin here, that means what? Output will be delayed, that is, if I delay this, if I shift it, if I delay this entire thing, so that this fellow goes here. Are you following this? If I shift it to the right by n minus 1 points, that means origin actually will go here, it becomes causal. But if I delay it by n minus 1 point, that means here I will be multiplying this by z to the power some amount, isn't it? Time domain shifting right means this, and therefore, R n, if its z transform is R z, capital R z into this into z to the power minus of this, that means from previous output whatever I was getting, that will get delayed by n minus 1. So, previous output was exactly I n, now it will be delayed. So, what will come out is I n minus this, but this is fine with me, because it is only a delayed version of what actually was transmitted, no loss of data. Okay. So, this introduction of this factor makes it causal and therefore realizable. Okay. This is where I think I stopped last time. Okay. Introduction of this delay factor, that makes it this thing realizable. Okay. Now, how does, if you want to construct this filter, you must know Hz. Hz comes from the channel model. That means, you must know the channel, you must know how the pulse values are, what the pulse values are, how the pulse values came. Originally, there was a pulse P of t that passed through the channel, physical channel of impulse response H of t, convolved, original pulse was distorted, zero forcing condition was destroyed, new pulse P prime t came, thus pulse values at various points, they gave rise to the samples H0, H1, H minus 1, all that were discussed last time. So, to know those values, you not only have to know original pulse Pt, but you must know the channel, then only you can find out P prime t. Okay. But channel is not known to you, further channel characteristics changes from time to time. That means, I have to try on adaptive means, which will learn from the incoming data about the channel impulse response and adjust itself. That means, what I will do, this Rn I will pass through an appropriate filter, FIR filter of coefficients W0 dot 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 Wp. How many coefficients? W0 will be for this, W1 for this, W2 for this, dot 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 Wp for here. Okay. I want this impulse response to come up. I want this impulse response to come up there, but I do not know this impulse response because I do not know the channel. So, what I do, I arbitrarily start with some values for this. Total number of points here, how many? 2 into n minus 1 plus 1, whatever it is, you call it p plus 1, W0 to Wp p plus 1. Okay. So, I have to find out these ones. So, what I will do, I do not know what their ideal values as shown in figure are. So, I start with arbit values. I filter them, find the error. Error between what? I want the output to be this, but I did not get the actual impulse response of this filter. So, I will get something else, not this. So, this will be my what is called desired response. That is, during the training phase, when the transmitter transmit universally known sequence, pilot sequence, training phase, receiver also knows. So, receiver knows what is transmitted. So, it is recorded with itself. It just delays it by this amount, gives it as a desired response, measures the error between the actual filter output plus and by this error, and this error is actually used in an adaptive algorithm. That is the topic of that is the subject to be studied here, adaptive algo. Okay. And this adaptive algorithm, what will generate? It will, from these weights, actually we show by this. What it does, suppose at a particular time index, say nth point of time, you have some weights W0 to Wp some value, you use them to filter, get the output, measure the error, take the error in the algorithm, this algorithm uses the error, and from the current value of the filter weights, it generates a new set of filter weights. There is a weight updation or weight adjustment, hopefully better choice of filter weights. And then again you filter this, again measure the error, and again feed it back to this adaptive algorithm, it again adjusts it further. Purpose is that to bring this one as close as possible to this, because I want this output to be this actually, I want this filters to be this only filter, isn't it. So, the error will be minimized, in that direction we will move, but in an iterative manner with time. At one point of time, you have got one set of weights filtered using the input data, using that, find out the output, take the error, use the error in the adaptive algorithm, then adjust the weights to get another set of weights, hopefully better set of weights. Again filter, again measure the error, again pass it feed it back to the adaptive algorithm, further adjust the weights, so on and so forth. It goes on in an iterative loop for several rounds of iteration, and hopefully it converges. That is, after some time you really get these weights very close to this, and we say it is converged. Once it is converged, okay, and sufficient training time for this training is given, so it is already converged, then again normal business starts. You no longer, transmitter no longer transmits the pre-designed training sequence, it transmits normal sequences. But now I can assume that I can trust the channel will start fluctuating now at least for some time. So, this will be the filter weights that are converged, they will indeed represent that ideal equalizer, and whatever I will get, that is indeed the one that is transmitted. Okay. Problem comes when you have the noise, because so long I took it only R n, but R n plus Z n, that actually goes to this equalizer, isn't it? This after convergence you get this equalizer, but R n plus Z n after during training, okay, you are training, but after training you are happy that okay, I have got a filter weights, a set of weights, and they got converged and all those things fine. I want to trust it, I want to use it, but now not only R n plus Z n are passing through it. That means there is a component from Z n also at the output. So far, I mean, often or many times this is not a problem, because there is a noise at the input, then noise will be passing through this filter, and there will be some noise at the output. I cannot, you see, I have to live with it. What I do, this will be then passed through a quantizer, because after all input labels here I n, they are not any continuous valued variable, either this symbol or that symbol or this symbol, like that, isn't it? Discrete values, like some various levels, 1 volt or 2 volt or 3 volt or 4 volt, like that. So, if you have a quantizer like that, and suppose indeed it is 1 volt, but because of noise it has become 1.1, still between 1 volt and 2 volt there is a huge gap. So, you can still make a correct decision. In the decision process itself, some effect of noise can go, because say around 1 volt you have got a slot, you have got a band 1.5 on the top and 0.5 on the bottom. So, within that band anything falling will be equated to 1. So, originally that receive sequence would have been 1, receive value would have been 1, but because of noise it is a 1 point something, 1.15, 1.3, 1 point or 0.8, 0.9, all will be quantized to the correct value only, isn't it? So, by the quantization process itself much of the noise will go, that is what we hope we could have been living happily with it. Sometimes there is a problem, that sometimes what happens, this equalizer, they show, especially the HZ channel model, HZ shows that it has got something called spectral null. Spectral null means something like this. If you take h to the power j omega, it dips, it almost touches 0. If you take the mod of it, touches 0, like that, dot 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 at pi like that. Okay. Sometimes it happens, it either goes absolutely to 0 or very close to 0. What does it mean on HZ? HZ is FIR, and the FIR filter, suppose it has got a 0 like this, 1 minus say A Z inverse into the remaining part, say H prime Z, concentrate on this. Suppose A is one minus A Z inverse means where is the root? 1 by A, is it at 1 by A, sorry at A, sorry, root is at A, is Z inverse, root is at A. Now, suppose A is, this is a unit circle and A is within unit circle, but very close to the unit circle, this is where your A is, this is A, and A is a complex number. So, therefore, this much is the magnitude of A, and this is the phase angle could be say theta. Okay. Now, H Z I am repeating again was this, some H prime Z. So, if you want to find out the frequency response, it will be 1 minus A e to the power minus j omega okay. This now suppose omega is changing, I move omega from 0 to 2 pi or minus pi to pi, any DTFT, any frequency response is periodic over 2 pi, all of you know, isn't it? That is basic DSP. So, it is enough to plot it from minus pi to pi. So, suppose I started at 0. So, that means 1 minus this a e to the power minus j omega. Okay. If you want, you can write it this way also, e to the power j omega, sorry, e to the power minus j omega, e to the power j omega minus a. This part concentrate on these factors. At omega equal to 0, I will say at any omega, this guy's magnitude is 1. This is one phasor, this is one phasor. This is a phasor difference, this much. When omega is 0, this minus this. So, this much. Then as omega increases, you are say here, then this much. So, the corresponding magnitude and phase that will determine, you will write it as a complex number. So, the corresponding magnitude part will come and a phase part will come. Slowly omega is increasing. As you see, as you are going closer to the point, the magnitude part of that phasor, difference phasor is decreasing, isn't it? And when you are aligned, that time the magnitude part has the minimum value. In fact, if this a is almost on the unit circle, magnitude part of that phase difference phasor will be almost 0, which means you will have a situation like this. Net magnitude, if you take the mod of this, there is mod of this, mod of this, mod of all the factors. Okay. So, mod of this transfer function will touch 0 or will become very close to 0. So, that means these spectral nulls indicate presence of roots, that is zeros, very close to unit circle in the z plane. Okay. Now, if that be the case, I was discussing Hz. So, this equalizer is 1 by Hz. So, that means there will be spectral peaks, zeros became poles, isn't it? Earlier it was just the phasor, the magnitude, the difference phasor magnitude, that is close to 0. So, overall magnitude of the response was 0 or very close to 0, but now it is not Hz, it is 1 by Hz. So, it is like 1 by 0 or 1 by something very close to 0. So, that will shoot up to infinity is a peak, isn't it? So, that means 1 by Hz into z to the power minus something, say minus some constant k. If you call it say h prime z, that means this will have peaks like this. So, which means noise will be enhanced. You see here, if it has peak, it has nulls, Hz has nulls, this has peaks, they will cancel each other. Okay. So, signal In was passed through first Hz, then 1 by Hz, Hz and 1 by Z cancel, In should come out as it is. But look at Zn, Zn does not pass through Hn, Zn passes only through this filter. So, Zn finds that okay, it suddenly is enhanced, because it passes through a filter which has only peaks. Are you following me? This is called noise enhancement effect in equalizers, noise enhancement effect. Okay. To cancel that, a modified form of equalizer is used, which I will just discuss and then I will get into the proper theoretical beginning of this course, because we are still going through the examples. That equalizer is called adaptive decision feedback equalizer. Normally, decision feedback equalizer, if it is made adaptive, it is called adaptive decision feedback equalizer. For the time being, again, I was not dealing with adaptive, because I assume 1 by Hz to be given, Hz known, 1 by Hz known. Adaptive part I did not, I had it separately. Okay. So, decision feedback equalizer, decision okay, decision feedback equalizer. Here what we do, this suppose this is the channel Hz, which is equivalent to Hn. I n is going through this. What they do, and here this is your S n. For the time being, I do not add the noise part. Otherwise, I would be adding a noise part Z n and all. For the time being, I will add later. What they do, you first use, these are the receiver side, first use what is called FFF. FFF means FIR filter called feed forward filter, just an FIR filter. You have to design it carefully. This FFF, maybe you can call it its impulse response, you can call it, this is H n, you give it name here G n. You design it such that what happens, this H n and G n, they come in cascade, isn't it? Channel H n followed by G n. G n is your construction, but that is at the front end of the equalizer. So, channel immediately after that G n. So, what is the overall impulse response? That is H n convolved with G n. At least you have done, some of you have done analog, and electrical people already know some DSP, I suppose, isn't it? Our students do not know, there is a, but electrical know. So, there will be this discrete convolution between H n and G n. You design the G n so that after, see, H n has non causality, this is H n, this is your H n, say something like this, and you are convolving H n with G n. What do you do? G n is a FIR filter. How do you do convolution? Suppose the FIR filter was like this, something like this. You reverse it and then go on shifting this way or that way and find out overlap from top and sample wise multiply and add. That is the way to convolve. You design it such that on this side, this is our result, on this side you have got very low value, almost 0, and at this point, from this point onwards you get something, some values up to some point. After all, 2 FIR convolved will give rise to an FIR only. So, it will go only up to some point. Okay. Suppose instead of so big, I draw it like this, say only 3 point, and on this side zeros. That is how we design. There are design equations and all. Okay, we design so that means together it is a causal system of this much impulse response. This is the sample of the equivalent impulse response at 0th point. It can have any height, but I can normalize to 1. That is, if it is say 10, I will have just a 1 by 10 factors. So, it becomes 1, that is important. So, I will constrain this to be 1, and then suppose these values are A, B, C. Then what I will do? This is my that quantizer, here only output decisions will come up. After all, it is an equalizer. So, finally, your processed sample has to be fed to the quantizer, that will say, okay, this is closest to that symbol or this symbol or that symbol, a decision will be made. This decision I will pass it through first a delay. So, past decisions will come up, and suppose I have a thing like this. What does it mean? Suppose past decisions are correct, suppose till this point of time your past decisions, that is decisions are correct. Right now you will make a correct decision, present decision, that I am coming later, but after this delay here past decisions will come. Suppose past decisions by hook or crook are correct, say they indeed correct values of I n which are transmitted are were detected like that, at least past 3. That means, here I have got correct value of I n, here I have correct value of I n, here I have correct value of I n, and they are multiplied by A, B, C and added, and then if this addition I subtract from this guy, what will I get? Look at this, these two together were forming this cascade, 1 A, B, C. That means, I n pass through just a simple system, FR system 1 A B C, that came up here. What is that then? I 0 into 1 plus A into I n minus 1, sorry, I n into 1. Can you see, or I have to, you know convolution, or you have to reverse it and shift it to the point n. So, I n into 1 plus I n minus 1 into A, I n minus 2 into B, I n minus 3 into C, that summation will come up here. That summation will come up, but here if I assume correct value of I n minus 1, n minus 2, n minus 3 available here, then they will be multiplied by A, B, C. Okay, they will be multiplied by A, B, C added, they will multiply A, B, C added and subtracted. So, what will be left here? No, I n into 1, only I n will be left, only I n will be present, isn't it? First portion I n minus 1, I n minus 2, that component is exactly subtracted. So, only I n will be left, and you pass it to the quantizer, it will happily quantize it to the I n, and it will be forming a loop in which it will work. And here I am no longer nowhere inverting the channel. So, even if this channel has zeros close to unit circle, I am not having that constraint that okay, zeros here become poles here, and therefore, spectral null means spectral peak, and therefore, noise enhancement. So, even if there is now noise added, some noise will propagate here and therefore here, but the spectral peak kind of thing will not come up, isn't it? So, in that quantization process, I can assume that noise effect to be minimized. It is a beautiful technique, you know. This is called decision feedback equalizer. Now, here again FFFGN and these coefficients, actually this is another FIR filter, isn't it? Input multiplied by A, one delay multiplied by B, another delay by C. This is another FIR filter. This is called FBF, feedback filter. So, this GN and FBF, these coefficients, how are they found out? First, here I assume that Hn is known, and therefore, you design an GN, so that you get things like this. And once this is known, then you take out A, B, C, and from this coefficient, isn't it? But that means you are assuming Hn to be known. But when in the case where Hn is not known, then again adaptively you have to find out Gn and this. Okay, that will make it adaptive decision feedback equalizer. So, this is another very important example for adaptive filter. There are plenty. Another example I forgot to mention today. Another example I gave that day, that was a smart antenna, beamformer. That is, in the same cell, I can give same frequency to two users located at two different directions, but by adjusting the antenna gains, I can form a beam in one direction and null in another direction. So that even though two users are using the same band, I can hear only one, other person cannot interfere, and if this person is in motion, my beam should lock on to them. So, it has to be adaptive. That is called adaptive beamforming. In the last class, I gave that example too. This gives you enough motivation, but I suggest that you go through the book by Heikin or Farang, or there is a book by the father figure of LMS algorithm called Widrow, Bernard Widrow and Stons. That is adaptive filter book. Plenty of copies are available in the library. And he gives lots of examples, very practical, very useful examples. On each example, there can be a course. Okay. So, just to get more and more practical motivation, you can go through some of the examples, very nice examples, and you can implement them in lab also. Okay. So, I will not go through this example thing anymore. What I will do, I will now get into the theory of the course. I tell you beforehand that this will be a mathematical course. Okay. Any question, Rajeev? Okay. No, you can go, if you want you can go, but let me go on with recording. Okay. This is a mathematical course. The mathematics that is required will be developed, almost like physics. It will develop without diluting any rigor. Everything will be developed, everything will be proved, but you have to have that love or interest in mathematical things, mathematical thinking, mathematical derivations. Our purpose will be to derive adaptive filter algorithms. This is a course on derivation of and also some performance analysis of adaptive filter algorithms. Okay. And domain is mostly statistics or stochastic process, because most of the time we will be optimizing something called mean square error. And the moment you have mean square error variance, immediately the E operator will come up, and therefore, all statistics will flow in. So, we have to start with some elementary notions of stochastic process and all. And another thing which I will need to make this course very neat and very nice is linear algebra, which all electrical and electronics engineers must know, but unfortunately here I do not know other department. In our department we do not have this course. Linear algebra is a key to signal processing, communication, control today. Okay. So, that also whatever linear algebra I need, I will develop in this course. Okay. So, whatever the amount of time that is left today, let us start with this stochastic thing. I am assuming you already know probability, statistics and all, but then I have to develop the things the way I want. You all know, say if we take a continuous valued real variable x, you know it has got a probability density p x, which is a non-negative function. What does p x means? P x into d x will give you the probability of the random variable x to lie. There will be, I am not writing everything, because then on writing I will be wasting too much of time. I am trying to go fast on this initial portion. I will not go so fast definitely when I go further, because things where I find there are repetitions or things which I expect students to know, I do not want to go slow. Anyway, this will be probability of x lying in x and x plus dx, that is p x dx, and it is such that p x dx integral is the total probability of x lying within the range. So, it has to be a global constant independent of whether it is x or y or any other random variables. That constant is taken as 1, all of us know that. Then if x and y, they are jointly random variables, two parameters which are random, but which have got some dependence between them, say temperature and humidity. So, then p x y is a joint probability density. What does it mean? That this into dx dy means the probability of x y lying in x and x plus dx simultaneously between y and y plus dy and simultaneously. Okay. So, once again if you double integrate it over the entire range of x and y, you will get, you have to get the same constant y and all that. Okay. Then you, instead of double, you can have multiple p x y j du v like that. So, okay. Next is, if instead of p x, suppose every time you are measuring the random variable x and there is some function given to you f of x, sin x, cos x, any some function. Every time x takes a value, you evaluate the function. So, that function also is random, because this argument is changing randomly. So, what is the expected value of the function? When x is lying between x and dx, you can approximate the function piecewise, constant function, it will take the value f x. But what is the, what is the probability? That times p x, isn't it? F x into, if its value will be f x, between x and dx, the function will take the value f x. I am doing that piece. Are you following me, or I have to draw? Suppose it is like this, you are here x, and between x and dx you are approximating it. Its value is f x, because dx is infinitely small. But what is the probability that I measure x and I get this much of f x? That means that into p x dx. Okay. So, that is the probability of x lying in this range. So, what is the expected value? That we integrate, okay, over the entire range. That is, within this range, expected value of f x is not just f x. F x I have to multiply f x by p x dx. That is the expected value, because it is not that every time I measure, I will get the function value equal to this much f x. Sometimes it is this much, sometimes not this. So, what is the probability of that function taking this much value? It is not f x, because always you will not get f x. So, it is f x qualified by another amount, modified by another amount, that is that p x dx. That is for any two, between any two value. So, if you have to do it from minus infinity to infinity, then we will get the average value of f x, is it average value. So, E, and then this is called E f x. E f x is f of x p x dx over the entire range. That will give the average value over the entire range. Earlier it was giving the expected value only in the small range. If you integrate over a finite region, it will give you the expected value within that region. Okay. that is, if you integrate it between one range and f x goes from one range to another range, what is the expected value of f x? You will get that is nice. Okay. Now integrate it. This all of you know. In general, instead of f x, if it is f x comma y, then E of x comma y will be f x comma y into p x y dx dy double integral, and you can extend it to any dimension. As an example, if z is complex, if there is a random variable z which is complex and both x and y are random, then E of z, again this z you can call as a function of x y after all, then E of z which is will be nothing but z or x plus j y times okay. So, this z will be called E of z will be called the mean or expected value or mean of the random variable z. So, instead of z you can just come to the original value x. What is E of x? X into p x dx. That is when the function is the value itself, f of x is x. When f of x is x itself, then E of f x means E of x, that is x into p x dx integral, that is called the mean of x, average of x. You all know that is just brushing up. Okay. Then, so you all also know what is meant by E of z if z is complex, because soon I will be dealing with complex valued random variables. So, now suppose you have got a random variable x which could be now real or complex, I do not care. E of x, we all know what is E of x. So, you cannot ask me what is the meaning of E of x, I have given you the definition, you knew already, but I am doing it in a systematic way. You call it the mean or expected value of the random variable x, and you call it mu x. Then around the mean, if you take this difference in general is complex. So, if you take the mod square of that, you will get a real quantity which is random, because even though mu x is constant, this is, so this differential it is a difference like AC, mu x is DC, this is AC. You take the square of that, every time that fluctuates because x value changes, and you take expected value of that, that will be a measure of the power, AC power, which is called variance. Variance is denoted like this. Okay. Then, if you take two random variables, jointly fluctuating random variables, maybe complex x, y, and if you take this quantity, this is called covariance, C x y, covariance between x and y. What is the meaning of this? If this quantity is high, suppose x and y are such, they are very much related to each other. When x is going above its mean, all that, y also going above. So, both the differences are positive, positive into positive, positive, or when x is falling below the mean, y also they are hand in hand. So, falls below the mean. So, both negative differences, again product is positive. So, either case if they are related to each other, you get a high value, but if they are very much uncorrelated, then this difference can sometimes be positive, this can be negative or positive, vice versa. So, if you take a huge number of cases and average out, you will get less value. That means, this will be a measure of the degree of correlation between the two random variables x and y. Okay. If two random variables x and y will be called uncorrelated if this quantity is 0. 0 implies x, y uncorrelated. What does it mean? If this is, you can expand this x into y star, mu x into y star, like that, 4 terms. You can take this product, no? There will be 4 terms. So, you have got one term like E x y star minus mu x y star E of that, mu x y star E of that. E you can take inside, mu x constant goes out. So, E of y star is mu y star. What is E of y star? E of y star is same as E of y then star, because E of y star also means y star into p y dy. P y is real, integral p y is real. So, you can put the star outside that way. These things I do not think I have to tell you people, it is very simple. So, mu x mu y star and then E of x into mu y star, that is E of x mu x again mu y star and mu x mu y star, both are random constant. So, no E on that. So, these two cancels, you are left with only this. So, if this is 0, that is if x and y are uncorrelated, this C x y 0 implies okay. If uncorrelated, then this quantity E x y star, this is called correlation between x y, denoted as R x y, correlation between x y. The order is important when they are complex. Between x and y, that means x first, y second, star on that. Between y and x means y first, y second, star on x. So, this order is important in the case of complex variables. Of course, for real x y and y x are same, no conjugate and all that, so you get the same thing. But for the complex case, x y star and y x star are two different things. Okay. So, if two random variables are uncorrelated, then their correlation is product of their mean, first one as it is, second one conjugated. Often we deal with zero mean random variables. Often we deal with zero mean random variables. In that case, if they are uncorrelated, if two zero mean random variables are also uncorrelated, that means correlation will be equal to 0, because 0 mean 0 into 0, isn't it? So, you can say that two zero mean random variables are given and their correlation is 0, then I can say they are uncorrelated, because this 0 can be written as 0 into 0 and 0 is, you can write it as mu x, you can write it as mu y star. So, this formula is valid. So, that means they are uncorrelated. If two zero mean random variables also have 0 correlation, then I can say they are uncorrelated. If their correlation is 0, they are called orthogonal. Now, consider a discrete sequence which is random, that is you are measuring some waveform. Waveform means sequence, you get a pattern, next time you measure you get another pattern, next time you measure another pattern. Every sample, say nth sample in each pattern is not repeating its value in all the cases, it is fluctuating. So, any sample is a random variable, changes with observation to observation. So, every sample is a random variable, that is a discrete random process. In that case, you take out say any particular one E of x n, you will understand the meaning of E now. E changes from case to case, mind you, like here it is simply if you take all this variable x, multiplying that by the corresponding probability density and integrating. If I bring in many, then joint density, all those can be avoided cleverly by using E, because before that is why I explained the meaning of E beforehand. E of x n, what is x n? You have got a sequence in a sample which is a random variable, because next time you measure the sequence it changes its value, next time it changes its value, so on and so forth. Okay. So, E of x n will be the mean of the nth sample. You can in general call it mu n, because that should depend on the point of measurement, time index. But often we model this random sequence is a stationary process. If it is first order stationary, it means this fellow is random, but its randomness is homogeneously distributed along this axis. That is, there is no bias, in the sense that maybe sometime in one experiment I get 0th sample to take very high value, next time or in next all occasions it does not mean 0th sample will still have very high value. Often it may have very low value, somebody else may have very high value, that could be at 100 location or 200 location or any location. Okay. So, the fluctuating property it is not localized, that okay, around this zone of the time axis the random variable will take very large values. So, mean is high, around this zone it will take very small values. So, around this zone this has a defined mean, very low mean, like that. If it is purely random, it does not know where its origin, does not care for this time axis, this randomness is going on as though from minus infinity to homogeneously. Then the mean thing, whether we measure at nth point or mth point or kth point, you should ultimately get the same thing. You can model that way, and this model is not, it is only an ideal model by the way. So, then it is called first order stationary process. First order because only x n, first order, no product, no square term or no product term. So, first order stationary. So, this becomes mu means first order stationary, n goes. Because the x n, I am not saying x square n, x cube n or x n into another value of x, degree of x is only 1. So, first order, mean is first order thing, stationary in the first order quantity. Actually, this is called first order moment. This E of x n is called first order moment, E of x square n is called second order moment, so on and so forth. So, if first order moment is stationary independent of n, then it is first order stationary. That is the language of pure statistics. Okay. Now, mean gone, fine. Another thing I discussed, the correlation, covariance and all that. Okay. Here if you take two samples, one is at nth point, another at a gap of k, and they are in general complex, and you have to find out the correlation between them. One is the nth sample, another is the n minus kth sample. Okay. So, first guy, second guy put a star if in general they are complex and take an expectation. So, this quantity in general should depend on what? The 2 points, nth point and n minus k means kth point, kth value, n is already known. So, it should be a function of two indices n and k. But suppose again I feel that, say that you see this degree of correlation which is given by this degree of correlation between these two samples. If I say that look, the process is such, its correlation property between samples should depend only on the gap, how far or how close, not where exactly they are located, whether they are these two or these two or these two or these two, because that correlating property also does not depend on particular zones of the time axis. That is, two samples are highly correlated or very less correlated, that should not depend on where in the time axis you are observing them. That should only depend on how, at what gap are they located, straight. If you model that way, then it should become only a function of k, and then it will be called, and this is a second order thing, product. There are only one term here, it says x square actually, second order, isn't it? So, if it is becomes a function of k, and you can call it r k, then it is called r k. Now, if the process is such, this is one extra thing, that is both first order stationary and satisfies this, then only it will be called second order stationary. But second order takes care of that, this is a subset of this. Okay. So, second order stationary or we call it wide sense stationary, wide sense stationary, WSS, wide sense stationary, if both the things are satisfied. E x n is just mu independent of n, the stationary in first order, and E is only a function of the lag k. The gap k is called lag, LAG, lag variable. Okay. This correlation has some properties, unfortunately time is just couple of minutes. You can see one thing, what is r minus k? And if I put a star here, the star here, star can go inside, After all, E means an integral with probability. So, I can put the star inside because probability is real function. The star goes means from here star goes, star comes here, n plus k if you call m, this becomes m minus k. So, x m into x star m minus k, again it is a function of k only. So, r k. So, that means for WSS processes r k and r minus k, they are conjugate symmetric. This is called Hermitian property, Hermition, Hermitian. R of k is same as r of minus k star. So, if it is real valued, no star business, r of k and r minus k are the same. So, it is an what do you call even function, isn't it, or symmetric function? R of k and r of minus k if they are same, it is symmetric, even function, okay. And it otherwise it is conjugate symmetric. In any case, this is called Hermitian property, okay. That is one thing. I think what is R of 0? R of 0 is which is the average power, both DC AC put together, no subtraction of mu. But if it so happens that we are dealing with zero mean processes, that is all the samples have zero mean and therefore mean stationary in mean, and then this is satisfied as a function of k only. If you consider this kind of processes, then E of mod x square is same as AC power only, okay, and then we will call it variance. For zero mean processes, this will be same as variance, well, no need to subtract the mean, and this is always greater than equal to 0 real. Correlation in general is complex. Please note these properties, I will make use of this in my derivations in future. Correlation could be complex, but R of 0 is non-negative real, it cannot be negative square. If it is equal to 0, that means at any n, E of mod x square equal to 0 means at every trial, take up any sample, it will take only 0 value, then only expected value also can be 0. A random variable, say random variable x n, mod of x n square or x, mod of x square, I am saying average is 0. That means, whenever you try x, its value should be 0 only, then only average will be 0. That means, it is a random variable which always takes 0 values, and then you can ask me, if it always takes 0 value, what is random about it? Now, this is something which you have to accept as a random variable. So, what statistics people do, they apply a trick. They call it, look, actually it is a random variable which takes 0 value with probability 1. You know, this is just a trick. So, here I will stop. I will discuss some more properties of this correlation, including Cauchy-Schwarz inequality and all, and little bit of spectral analysis. Then I will directly move into what is called Wiener filter or optimum filter. Okay. And from optimal filter to LMS algorithm for the real case and complex case. So, we will have a headlong, you know, entry into adaptive filter. Okay. Yeah.
So, why are you calling this as power R0 expectation of, because that is the ensemble average. Power is something related to time, right?
No. Power actually for random thing I should only have this. The time thing is a follow up. Power means what? A random variable is given. I will treat at the look at the sample purely as a random variable located at nth point. Because of stationarity assumption, you get the same value whether it is n or m or l or k, but this value is changing from time to time. I mean, this observation, this one value, next observation, high value. So, it is changing. So, what is the average power of that particular sample? Okay. Then there is a concept called ergodicity. That, since you are asking the question, I will use the notion of ergodicity in the next class. They are under, I have to explain the physical meaning of ergodicity. There, this ensemble average can be obtained by time average, and then you use that, because in real life you cannot go on waiting for many experiments and then calculate the ensemble average and all, isn't it? So, in ergodicity, using one sequence only, using temporal average, time average, you can find out this. But anyway, time is up and recording. So, either these questions, I repeat that when you cross the time, we cannot enter any question within the time frame, we can discuss outside, offline. Okay. So, that is all for today. Thank you.